The Standard Model Effective Field Theory (SMEFT) is a crucial tool for exploring non-standard model physics at the LHC, particularly in the absence of new light particle discoveries. It is constructed as an expansion in higher dimension operators, with the SU 3 times SU 2 times U 1 gauge symmetry unbroken. The SMEFT Lagrangian is expanded to dimension 6 operators, and the Warsaw basis is used to parameterize the new physics effects. The calculations are performed using the Feynman rules from Ref. 2, assuming a diagonal CKM matrix and real operator coefficients. The Electroweak precision observables, EWPOs, considered are the Z and W boson pole observables, which receive contributions from 2499 baryon number conserving dimension 6 operators in the Warsaw basis. However, only a subset of these operators contributes to the EWPOs at tree level and NLO. The tree level contributions come from 2 bosonic operators and 8 fermionic operators, while the NLO contributions arise from 22 additional operators. The fermionic operators are categorized into 2 fermion and 4 fermion operators, with specific flavor structures contributing to the EWPOs at NLO. The 2 fermion operators have diagonal flavor structures due to the assumption of a diagonal CKM matrix, resulting in 3 independent coefficients for each operator. The 4 fermion operators are classified into several categories, with some exhibiting flavor symmetry. The explicit forms of the operators contributing to the EWPOs at tree level and NLO are listed in Table I and Ref. 27, respectively. The operators modify the couplings of the Z and W bosons to fermions, and their effects on the measured quantities are given in Appendix A of Ref. 27. The relation between the VF, V, and the Fermi constant G_F is also affected by the dimension 6 operators involving the electron and the muon. The calculations involve the use of equations 2 and 6, which describe the expansion of the observables in terms of the SMEFT operators and the modification of the Fermi constant, respectively. The results are presented in a way that allows for the extraction of the operator coefficients, which can be used to constrain new physics effects. In the Standard Model Effective Field Theory (SMEFT) framework, the authors analyze the structure of 4 fermion operators, focusing on flavor symmetry and its implications for electroweak precision observables, EWPOs, at next to leading order, NLO. These operators are classified into 2 categories, Class B, involving identical fermion representations, and Class C, involving 2 different fermion representations. The coefficients of these operators have specific flavor structures, constrained by the requirement that the Kabebo-Kobayashi-Maskawa, CKM, matrix is the unit matrix. The authors derive the flavor structures for each class, resulting in 9 independent coefficients for each operator in Class B and 11 independent coefficients for each operator in Class C. To reduce the number of operators, they consider different flavor assumptions, including a U(3)5 symmetry and the minimal flavor violation (MFV) scenario, which assumes that the only source of breaking of the U(3)5 symmetry is the Yukawa couplings. Under the U(3)5 symmetry, the operators in Class A respect a specific form, and there are 7 real coefficients in this class. The coefficients of Class B reduce to 11 independent coefficients, while those of Class C reduce to 11 independent coefficients as well. In total, 29 independent coefficients contribute to the EWPOs at one loop. The MFV scenario, with a massless B quark, is equivalent to a global U(2)5 symmetry. Here, 12 independent coefficients contribute to the EWPO at NLO, and the number of independent coefficients in Class B is reduced to 17. The authors present the resulting flavor structures and the number of independent coefficients for each class of operators under the different flavor assumptions. These results will be used to constrain the SMEFT coefficients and predict the EWPOs at NLO. The authors also classify operators into 3 classes. A, B, and C. Class C operators have 2 top quarks and satisfy specific relations, resulting in 21 independent coefficients. They explore 3 scenarios: 3rd-generation centric, 3rd-generation phobic, and 3rd-generation phobic plus U25. In the third-generation centric scenario, only operators involving the third-generation fermions are non-zero, resulting in 9 real coefficients in class A, 5 coefficients in class B, and 11 coefficients in class C in the third-generation phobic scenario. New physics only couples to the first 2 generations, leading to 14 independent coefficients in class A, 23 coefficients in class B, and 44 coefficients in class C. Finally, the third-generation phobic plus EWPOs scenario assumes both a EWPOs symmetry and new physics coupling only to the first 2 generations, resulting in specific flavor structures for each operator class. Throughout these scenarios, the authors emphasize the importance of flavor assumptions and symmetries in constraining the number of independent coefficients and operator structures. The counting of coefficients and operator structures is in agreement with previous works, specifically Tables 2 of 20 and Table 9 of 19. The author's analysis provides a comprehensive understanding of the flavor structure of operators contributing to EWPOs at NLO, highlighting the significance of flavor assumptions and symmetries in precision electroweak calculations. The authors classify operators in the Standard Model Effective Field Theory (SMEFT) into 3 classes, A, B, and C, based on their flavor structure, which affects the number of independent coefficients contributing to next to leading order NLO predictions for electroweak precision observables (EWPOs). In the flavorless scenario, 26 coefficients contribute to EWPOs. The authors generalize the flavor structure of each observable and perform a new calculation for many flavor structures and observables, including Z decays to fermions. The SMEFT Feynman rules and Feyn rules are used to generate one-loop and real emission amplitudes, including QCD and EU corrections to the Z and W pole observables. The gauge invariance of the final results is verified explicitly. The amplitudes are manipulated using Feyn calc, and the integrals are reduced in terms of Passerino-Veltman integrals, retaining only terms of O, V squared, lambda caret 2. The authors calculate Z decayed to 2 fermions in the SMEFT framework, focusing on real and virtual contributions. Real contributions arise from real photon and gluon emissions, which are necessary to cancel infrared, IR, divergences from virtual contributions. Virtual contributions consist of the full set of one-loop electroweak, EU, and quantum chromodynamics, QCD, diagrams with SMEFT vertices. To treat ultraviolet, UV, divergences, the authors use dimensional regularization in d dimensions, cancelling the poles with appropriate counterterms. They choose to exactly cancel all tadpole contributions, identifying the renormalized vacuum with the gauge-dependent minimum of the renormalized Higgs potential. The coefficients of the dimension 6 operators are treated as MS parameters, constructing renormalized coefficients C, mu. The one-loop anomalous dimensions ij are defined, which are not diagonal, and 4 fermion operators mix with 2 fermion and other operators under renormalization. Here is a combined summary of pages 13-16 of the research paper. The authors derive the hadronic contribution to delta R, which is defined as delta R underscore had, mz, equals 4 pedia, mz, da, 0, using dispersion relations and experimental data. They then relate the mass of the W boson to input parameters in the Standard Model, SM, and the Standard Model Effective Field Theory, SMEFT. The authors define several quantities, including delta R underscore W, delta R, G1, G2, F1, and F2, which enter into the definitions of the W boson mass. At next to leading order, NLO, the mass of the W boson is calculated as M underscore W. NLO equals SQRT, M underscore W squared. SM plus 1/16 pi caret 2 G underscore F, M underscore W squared. Eft, H underscore Q. Where H underscore Q is a function of M underscore W squared. SM and M underscore W squared. Eft. The authors calculate M underscore W squared, SM and M underscore W squared. Eft at one loop and use the best theory result for M underscore W squared. SM to obtain their final expression for the mass of the W boson. The authors also discuss the calculation of other observables that depend on the mass of the W boson, using their best knowledge of M_W in the calculation of the leading order, low, contributions and M_W NLO in the calculation of the NLO contributions. They remark on the validity of their expansion, noting that after renormalization, the amplitude is finite, and they retain only terms that are linear in the SMEFT coefficients. The authors present a methodology for deriving limits on SMEFT coefficients that depend on assumed flavor scenarios, considering one non-zero operator type at a time and imposing flavor symmetries. They provide an example of this procedure for the coefficient C(1, QQ) in the MFV scenario and present a table comparing experimental and theoretical values of various electroweak precision observables. The authors discuss limits on two fermion operators that contribute to Z and W boson observables, comparing LO and NLO results for SMEFT coefficients in various flavor scenarios. They also present tables and figures showing the 95% CL limits on coefficients in various flavor schemes for Class B and Class C operators, noting a strong dependence on the flavor scenario. Overall, the authors demonstrate a methodology for deriving limits on SMEFT coefficients that depend on assumed flavor scenarios, highlighting the importance of considering flavor assumptions when deriving limits on SMEFT coefficients. The study investigates the limits of coefficients of two fermion operators in various flavor scenarios, including U3-5, minimal flavor violation, MFV, third-generation centric, third-generation phobic, and flavorless scenarios. By marginalizing over independent flavor structures, the results show that the flavorless scenario yields the most precise limits, with factors of 10,100, more precision than in MFV or U3-5 scenarios for certain coefficients. The limits on Class B operators are also presented, with the flavorless setup yielding similar results to MFV and U3-5 flavor structures. The study highlights the sensitivity to flavor assumptions and the importance of including flavor dependence in the analysis of dimension 6 SMEFT operators. The results are interpreted as bounds on dimension 6 SMEFT operators, relevant for beyond the standard model, BSM, physics. Measurements at the Z and W boson poles provide important limits on BSM physics, with bounds on anomalous particle couplings extendable to systematically include NLO QCD and EU effects. Numerical results for electroweak precision observables, EWPOs, are presented to NLO in QCD and electroweak interactions for arbitrary flavor structures of 2 fermion and 4 fermion operators. Figures 810 display limits on sample coefficients of Class B and C4 fermion operators in different flavor scenarios, with significant correlations between flavor structures observed. The flavor structure has a substantial impact on the bounds derived on 4 fermion operators, which first contribute to EWPOs at NLO. Ignoring flavor typically leads to tighter bounds on SMEFT coefficients than in a general flavor scenario, with the presence of a top quark in internal propagators generally leading to stronger constraints. This study delves into the constraints imposed by Higgs, Dibison, and electroweak data on flavorless and flavorful 2 fermion operators within the Standard Model Effective Field Theory, SMEFT. The analysis is performed at the next to leading order, NLO, in the strong coupling constant, providing a more precise picture of the allowed ranges for the Wilson coefficients of these operators compared to leading order, LO, analyses. The results are presented in tables IV and V, categorizing the operators into 2 classes. Class A, which includes operators not subject to electroweak precision data constraints, and Class B, which includes operators constrained by both Higgs and electroweak data. Class A operators exhibit significant improvement in precision, while Class B operators show less improvement due to weaker constraints from electroweak data. The paper emphasizes the importance of considering flavor structure, as certain flavor assumptions can lead to more stringent constraints on the Wilson coefficients. It also discusses the limitations and future directions of the analysis, highlighting the need for a comprehensive treatment of theoretical uncertainties and the importance of incorporating additional experimental data to further refine the constraints on SMEFT parameters. The study explores NLO results for 95% confidence level limits on Class C operators, utilizing tools such as Fein rules, Fein arts, and Fein calc for generating Feynman diagrams and amplitudes. It also employs FEYNCALC and Tarasov's generalized recurrence relations for two-loop propagator integrals with arbitrary masses to evaluate two-loop self-energy basis integrals using differential equations. The paper presents a comprehensive list of references, including works on the Cabibbo angle anomaly, minimal flavor violation, and electroweak precision observables. It also discusses the NLO QCD corrections for Higgs boson production at hadron colliders and the evaluation of two-loop self-energy basis integrals using differential equations. The study concludes by emphasizing the need for further research, particularly in the context of the MF-SMEFT and the role of flavor in new physics models. In the context of precision electroweak measurements, the authors provide a comprehensive analysis of standard model effective field theory, SMEFT, coefficients under various flavor assumptions. They emphasize the importance of considering flavor assumptions and next to leading order, NLO, corrections in SMEFT fits to precision electroweak data. The authors present 95% confidence level limits on the SMEFT coefficients C phi Q, 3, and C phi U, as well as C phi D, IJ, C phi E, IJ, C, 1, L, IJ, and C, 3, L, IJ, in different flavor scenarios such as minimal flavor violation, MFV, third-generation centric, third-generation phobic plus U25, and flavorless scenarios. These limits are obtained at both leading order, low, and NLO in QCD corrections. The results demonstrate the significant impact of flavor assumptions on the limits of the Wilson coefficients, with NLO calculations generally yielding more stringent limits than low calculations. The flavorless scenario often results in the most stringent limits, as it assumes that all flavor coefficients are equal. The presented limits provide valuable constraints on the Wilson coefficients, which are essential for understanding the underlying physics beyond the standard model. The authors also discuss the importance of a consistent and systematic approach to constrain the SMEFT coefficients and explore the implications of precision electroweak measurements for beyond the standard model physics. This comprehensive analysis contributes to the ongoing efforts to understand the nature of electroweak corrections and their role in shaping our understanding of the standard model and potential new physics beyond it.